Okay, this is the first video for chapter 10, which I think is just entitled The Shapes of Molecules. Yeah, it is, The Shapes of Molecules. So, as we go, I'm going to explain why molecular shape is important. It turns out it's definitely important in biology. It's important for many things. But you'll see that it's kind of in some ways, it's kind of a fun technique because there's a lot of problems in chapter 10 that we'll encounter here, which kind of start out like this. Here's a name of a chemical molecular formula and a chemical name for a molecule. And you need to predict what its shape is and using various techniques. And so I'm actually going to jump in and kind of teach you some of these techniques and discuss them without really kind of even talking about shape yet. We'll talk about shape a little bit later. But I kind of want to introduce you to some of the techniques that we'll use to solve problems like this. The first one is called the Lewis structure, or something that's called the Lewis formula. It's named after a scientist named Lewis. If you remember, we actually were first introduced to something similar to this, I think last chapter. It was called the Lewis dot structure. And what that was, just to recap, is focusing on an atom and its valence electrons only. And so it was a way of depicting what for example, a carbon atom looked like. A carbon atom could be represented as this in the Lewis dot notation, which is essentially saying carbon has a nucleus, obviously, and it has a bunch of inner shell electrons. But in its valence shell, there's 4. And so you can kind of depict it this way. So the Lewis structures kind of take this a step further, and I'm sure you read this in the book, but let's kind of go through that together. So so here's the technique of determining a Lewis structure of a molecule. Yeah, okay. So I'm gonna make one note that I just thought was awesome. So the first step is someone says, okay, here's a molecule, and we'll start with an example of carbon tetrachloride, which looks like CCl4. Okay. So the first technique is to say, all right, figure out which one of these atoms you want to make the center atom. And it's not you want to make, but in some cases you have a choice. In this particular case I'm using, you don't really have a choice. There's going to be one of these atoms that's going to be in the center, and the other atoms are going to be around it, bonded to it, around it. And the technique is, generally speaking, you start with the least electronegative. Now, if you remember, electronegativity is elements are more electronegative when they're to the right of the periodic table, and as you go to the left, they become less electronegative. So in this case, clearly carbon is less electronegative than chlorine, which is quite electronegative. So basically, the first step is to find the least electronegative atom and put that in the center of your diagram. And I can tell immediately I want another pen. And I don't have one. That's not so good. All right, I'll just stick with this one now. Okay, so here's carbon in the center. I have one somewhere. One moment. Well, maybe I'll use red here. See if red's any better. All right, so carbon's in my center. That look okay? Yeah. And then I'm going to arrange the 4 chlorines around the carbon. And this is the technique. So you start with the formula, you arrange the atoms, start with the center atom being the least electronegative. Then in this formula you count the total number of valence electrons. Okay? So in this case, carbon has 4, and each chlorine has 7 valence electrons, each one. So we basically have 4 times 7, or 28, for a total of 32 valence electrons. Okay? So after we have this shape, what we do is we draw a line connecting the center atom to each of the other atoms. And that line represents 2 electrons. Okay? So essentially this is a pair of electrons that is being shared in a covalent bond between the center atom and its chlorine atom. Okay, so out of the 32 valence electrons, by drawing these little single bonds here between the carbon on each of its chlorines, we've consumed 8 electrons. Okay. Now the next step is fill in the rest of the electrons. And this is actually one that takes a little creativity sometimes, because sometimes there's more than one way of solving this. But take the rest of the electrons and add them to the atoms such that each atom ideally has exactly 8 electrons around them. If you remember from the previous chapter, 8 electrons, 8 valence electrons is a very stable arrangement for many atoms, especially these atoms that are in the these nonmetals that are in the upper end of the periodic table, like carbon and nitrogen, and again all the elements that are common in organic chemistry. So the Lewis structure makes heavy use of this octet rule. Octet meaning 8 electrons. So we want to try to have all these atoms to have 8 electrons around them. Well, first of all, carbon already has 8 the way I've drawn it, because again each of these lines represents 2 electrons. So 2, 4, 6, 8. Carbon's fine. I'm not going to add any electrons around carbon because it already has 8. But we have how many to go? 24 left. Well, okay, chlorine, each chlorine so far only has 2, so I'm going to add a pair of electrons around this chlorine atom. 1, 2, 3, 4, 5, 6. And I'll do the same thing here. 6 more. And then over here, 6 more. And then over here, 6 more. So I added 24. That's perfect. That's exactly it. So I'm all done. I have no more electrons to add. This, and now I'm going to do a check to see at this point do all of the atoms have 8 electrons surrounding them? And we already checked carbon. Each chlorine has a 2 in the valence bond here. Sorry, in the covalent bond. And then 3 more pairs of lone pairs, basically non-bonding electrons, to make 8. Each one has 8. So we're set. So carbon tetrachloride, this is the Lewis structure for carbon tetrachloride. Okay. So this is kind of how it goes. Let me do another one as another example. Okay. Let's do as a second example ammonia. Good old NH3. Okay, for ammonia, we'll start with the least electronegative atom, which, by the way, you never start with hydrogen. Hydrogen is never a central atom. And so N will be in the middle, and then I'm going to put the H's around it. All right, let's count. Our next step is counting our valence electrons. Nitrogen has 5. And hydrogen has 1 each, so it'll be 3 times 1, for a total of 8. Okay, so I've already drawn 2, 4, 6 of them when I drew these little lines here. So I only have 2 electrons to go. Well, let's see. Following this octet rule, you can see that nitrogen has 2, 4, 6. Let's put the pair there. Okay, and voila, we've got ammonia. So in this case, the nitrogen atom has an octet electrons around it, and each hydrogen has 2. Now you'll see the hydrogen is an exception to the octet rule. There are several exceptions to the octet rule. I wonder if I can cover them now. I bet I can. I'm going to try to cover them right now. Hydrogen is the first and most common exception to the octet rule. Hydrogen is so light and so small that, and if you remember from an orbital perspective, hydrogen only has access to the 1s orbital. So there's really, it can't even have 8 electrons around it. It can only have 2. So hydrogen is the first exception to the octet rule, which is that elements in the first row of the periodic table, hydrogen and helium, can only have 2 electrons, not 8. Okay, so that's the first rule, first exception to the octet rule. The second exception to the octet rule is that some elements that are, I'm going to call them electron starved, meaning they don't have very many electrons anyway, will oftentimes have fewer than 8 electrons surrounding it. Classic example of that is boron. And let me actually draw boron real quick. I'll draw boron tetrachloride. Okay, and I'm going to fill it in quickly here, but you could do the valence electron count, and you'd find that, sure enough, boron has 3 valence electrons. 1, 2, 3 of this adding there. Chlorine each brings 7. This is how boron trichloride, sorry, I said tetrachloride, boron trichloride would look. But if you look at boron in the middle, we'll get a new pen here, I promise. It only has 2, 4, 6 electrons around it. It doesn't have an octet. And that's this is one of these exceptions. For smaller atoms that are electron starved to begin with, oftentimes you will not have an octet around them. Okay. The third exception to the octet rule is that some electrons actually don't even have fully paired electrons. They have what are called unpaired electrons, or also known as free radicals. We talked about this, I think, in some previous videos. So for situations that involve free radicals or unpaired electrons, then you'll obviously, one of those atoms will end up having an odd number of electrons, and therefore not a full octet. And then the last exception, and a pretty important one when we get to start in the subsequent videos when we talk about shapes, there are some atoms that are heavier, meaning they're further down the periodic table, that will actually have more electrons than 8. And there's a kind of a fundamental orbital reason. If you remember when we were talking about our orbitals, for example, in the second row, gosh, dog it, I gotta get a better pen. For example, carbon has access to the 2s orbital, actually 2 electrons, and the 2p orbital. There's 2 electrons for carbon there, and so, but it doesn't have access to a 2d. There is no such thing as a 2d. D doesn't come about until you get to the where n equals 3, if you remember the quantum numbers. So for carbon, there can only be an octet. There can't be any more because there's not enough orbitals to hold all those electrons around carbon. However, when we get down to that third row of the periodic table or higher, there's access now. Like for example, take silicon, which is just right below carbon. It has a 3s orbital, which has 2 electrons, and it has a 3p orbital, which has 2 electrons. And but there's also a potential for a 3d orbital. And so all that means is that it's possible to have more than 8 electrons around one of these larger atoms. And again, you'll see this coming up because there's some important examples when we get into shapes. Okay, that is the end of this video. I'll pick back up in the next one. We'll talk a little bit further about Lewis structures.